Welcome friends for our new lecture in green chemistry. In this lecture we will be concentrating on phase transfer catalysts. In the last lectures we have seen about the principles of green chemistry, we have seen about the green catalysts and we have also seen about the green reagents. Now we will be concentrating on another type of green catalyst, that is phase transfer catalyst. We have seen green catalysts. These three types of green catalysts we have seen it in the last lecture, that is acid catalyst, basic catalyst and oxidation catalyst. In this lecture we will see more about the phase transfer catalyst, while the next lecture we will concentrating more on the biocatalysts. Organic reaction, when we are doing it, there are certain problems that are encountered in the organic synthesis, like for example substitution reaction, a simple reaction such as substitution of 1 chlorooctane with sodium nitrile in water. We find that it is not proceeding to what extent we want it, because when we are stirring this for several days, then also there is no significant amount of product being formed over here. This is because the substrate that we have it, or the reactant that we have, 1 chlorooctane, this is soluble in organic solvent, aprotic solvent. It is soluble in 1 chlorooctane, while our reagent that we are using, sodium nitrile or sodium cyanide, this is soluble in water. It is not soluble in organic solvent. So the reagent is not able to contact with the reactant. So in this cases, the reaction, whatever happens, a small amount of reaction that might happen, that reaction is happening at the interface only, not at the, if this is our organic layer and if this is our water layer, then Cn minus ions will be present in water, while our chlorooctane will be present in the organic layer. So whatever the molecules are at the interface only, those molecules on the interface, they will only be reacting with the cyanides. So reaction will be very slow and we will not be obtaining the product. These reactions happens, or we encounter such problems many a times because our organic reactants are soluble in organic solvents, whereas our reagents are either inorganic compounds, so they are insoluble in organic solvents and they will be soluble in water. So to overcome this, these systems are all dibasic systems or biphasic systems. We have two phases are present in this. So as there are two phases are present, we need to have a certain material which will bring a reagent from one phase to another phase. If we can bring a certain material whereby this reagent can be brought into organic layer, or the reactant may be brought into the aqueous layer, in that cases then the reaction will become faster. So we need such catalysts. We know that the catalysis is a process of increasing the rate of chemical reaction by adding a certain substance called as catalyst. As these are biphasic systems, so what we need is exactly the catalyst we need in such a way that they will be bringing our one of the reactant, or either reactant or a reagent, from one phase to another phase. So phase transfer catalysis refers to the reaction between two substances located in different immiscible phases. They are located in two different phases and in presence of a catalyst. That is, phase transfer catalysis is the process in which the catalyst is bringing one of the reactant into the another phase, from one phase to another phase. The catalyst that we are using is called as a phase transfer catalyst. This phase transfer catalyst facilitates the migration of a reactant from one phase to another phase when the reaction is occurring. As there are two phases are involved, this reaction or this catalysis is called as a heterogeneous catalysis. The reaction that we were looking after, that is a substitution reaction, which was reluctant to proceed in a biphasic system when we are not adding any catalyst over here, when we are adding simple NaCN and chlorooctane in water and decane. When we are doing it, water and decane are immiscible solvents, so reaction was not proceeding. But in presence of a phase transfer catalyst, if we do the add a small quantity of phase transfer catalyst, then this reaction proceeds within 2 hours and at a moderate temperature of say 105 degrees Celsius, and the reaction will be proceeding up to 95% yield. So reaction proceeds very rapidly, and we get the reaction goes for completion, and we get the product in an ample amount. So these phase transfer catalysts are the ones which we are using it in such a way that they will be bringing one of the ions from one phase to another phase. So one of the reagents, either reagent or a reactant, from one phase to another phase, when they are bringing it, that we call it as a phase transfer catalysts. The advantages of phase transfer catalysts are numerous. We will see few of them. That the phase transfer catalysts do not require vigorous conditions, and as they are not requiring rigorous conditions and they are catalysis, so the reaction becomes faster. As it is a catalysis, so it will be bringing the reaction. It will try to form the product via a different mechanism. So as the product is formed via different mechanism, it will be lowering the energy of activation, and so more number of molecules will be able to cross over the activation energy barrier and will be forming products to a larger extent, and it will be rapid products will be formed. And also it do not require aprotic solvents, which are expensive solvents, like for example DMF or DMSOs. Dimethyl sulfoxide and dimethyl formamide, these are highly expensive solvents, and so they will increase the cost of manufacturing, and also these are difficult to remove. Also they are having high boiling points, so it will be very difficult to remove them after the reaction has occurred. So this PTCs has an advantage that they are using normal aprotic solvents can be used over here, like decane or petroleum ether, or even we can use it alcohols and simple other solvents, we can use it in the reaction. Similarly, the reactions are usually occurring at a lower temperatures. As the temperatures are lower, so it has advantages. Green chemistry wise also it has advantage that there will be lesser amount of energy requirement. When we are not increasing the temperature, it will be having lesser amount of energy requirement will be there. As the energy required is lesser, so the synthesis becomes more greener. Similarly, there is no need of anhydrous conditions, as water is one of the solvents. So we will not need to maintain the anhydrous conditions here. Normally when we are using aprotic solvents, the organic synthesis needs to be carried out under anhydrous conditions, while when we are using water as one of the solvents, so there is no need of maintaining this anhydrous conditions there. Similarly, with the help of PTC, that is phase transfer catalyst, anion is available in aprotic solvent, and hence its nucleophilicity increases. This is very much important. This concept we have seen it in the leveling effect in our postgraduate classes. Leveling effect, that is anions or the acids, when we are taking it in aqueous medium, they can have it with pH within 1 to 14 only. But when we are changing the solvent, when we are changing the medium from aqueous to organic medium, when we are going, the range will be increasing, range of pH will be increasing there. And similarly here also, when we are using nucleophile or an anion, so that nucleophile will have a certain nucleophilicity in water, because the strongest nucleophile in water can be only hydroxide ions. Whatever other strong nucleophiles we will be adding, it will be generating OH minus ions in water. But when we are using another organic solvent, there the nucleophiles will be different, and so we will get the nucleophile will increase its nucleophilicity. Similarly, when an anion is present in aqueous medium, it is greater amount of solvation is there. Greater amount of solvation is observed in aqueous medium. But when we are adding the same anion, if it is made available in organic solvent, the organic solvent being non-polar, it will not be able to solvate it. So the nucleophilicity of that anion increases in organic solvents, thereby increasing the rate of reactions. The workup procedure in phase transfer catalyst is very easy, very simple. As we are using organic solvents, so our product will remain in the organic medium, and it can be easily removed through just simple evaporation. Also we can remove it, because we are using solvents which are having low boiling point, so it can be easily removed from there. Use of strong bases is avoided. Strong bases like methoxide or ethoxide ions is avoided here, because we can use very simple bases also that will be able to catalyze the reaction faster. As this will increase the nucleophilicity in the organic reaction, so simple mild bases can also have higher activity there. Similarly, except water sensitive reactions. Except water sensitive reactions, all other reactions can be carried out by using phase transfer catalyst, because in phase transfer catalyst one of the solvent is water. So we need to be careful that we are not able to do the water sensitive reactions using phase transfer catalyst. Water sensitive reactions are like, for example, when we are using N-butyl lithium as one of the reagents. N-butyl lithium or any alkyl lithiums are all water sensitive reagents. These are highly explosive when they are coming in contact of air or water. When they are coming in contact of air or water, they will explode and accidents will be occurring. So whenever you are using such reagents, you have to be very careful that they are not coming in contact of even air also. So you have to be very careful while using such reagents. These reagents we will not be able to carry out the reactions with these reagents cannot be done via phase transfer catalyst, but all other non-water sensitive reactions can be carried out using phase transfer catalyst. As the phase transfer catalysts are in two phases, green solvents can be used instead of toxic solvents. As these are biphasic reactions are there, so we have a greater choice of solvents from where we can choose. We do not need to have a toxic solvents, or we do not need to have a aprotic solvents. We can use it simple non-polar solvents also, which are greener in environment. So we can use the greener solvents instead of toxic solvents. Similarly, phase transfer reactions are rapid. They proceed through less energy of activation and hence making the synthesis greener. They are having lower temperatures also, so energy requirements are low. They are using catalysts, so they are also having greener principles. They are following it here. Similarly, as the reactions are carried out at low temperatures, they are having greater selectivity and lesser byproduct formations are obtained. This is very important when we are conducting reactions, when we are doing organic synthesis. Generally in organic synthesis we come across formation of unnecessary byproducts. So multiple products are formed and then we have to separate those products from the desired product. So it will be adding steps in the workup. So when we are doing a reaction at lower temperatures, there is a greater amount of selectivity is there, because the reactant molecules are not so reactive. As the temperatures are lower. As the temperatures are increasing, its energy increases, and as the energy increases, they will have greater reactivity will be there, and as the greater reactivities are there, there will be lower selectivity will be there. This is very much similar to what we feel it when we are getting hungrier. If we are having, if we are more hungry, then we will eat whatever is coming front to us. Whatever is nearer to us, we will pick it up instead of choosing the food, whether we like it or doesn't like it. When we are hungry, then we will just grab the food that is present nearer to us. But when we are having less hunger, when we are, our stomach is almost type of a full, so we will choose which the items, our food items which we will like it. So we becomes more choosy, or we becomes more selective. So when the energy is lesser, the reactants will become more choosy, or they will become more selective. Hence the selectivity will increase if the reactions are at lower temperatures. If the reactions are at higher temperatures, selectivity is lesser. So as in the when we are proceeding with phase transfer catalyst, lower temperatures are being required, so it leads to greater selectivity, and as the greater selectivity is there, desired product will be formed in greater quantity and lesser byproducts are formed. So thereby we will be having more profitable products are formed. So these are few of the advantages of phase transfer catalyst. We will see the few examples of phase transfer catalyst. There are numerous examples being reported of phase transfer catalyst. Industries are nowadays using this phase transfer catalyst in a very large amount, because they are making the processes profitable processes, and the reactions are rapid. The advantages that we have just seen it here. we will look into phase transfer catalysts such as the tetra-N-butyl ammonium halide, where the nitrogen is attached with 4 butyl groups, or trimethyl benzyl ammonium chloride or triethyl benzyl ammonium chloride, either trimethyl benzyl ammonium chloride as TMBA or triethyl benzyl ammonium chloride or TEBA. Both these reagents are used as a phase transfer catalyst. Then we will also look into Aliquat 336, that is methyl trioctyl ammonium chloride. There is one methyl group attached to nitrogen and 3 octyl groups are attached to nitrogen. So these are is called as a Aliquat 336, or it is also called as a Stark's catalyst. This is also known as Stark's catalyst or Aliquat 336. Similarly, we will see compounds like crown ethers, which are ethers, cyclic ethers containing 5, 6, 7 oxygen atoms in the cyclic ring. So these are having greater advantages in carrying availability in making available the anions in the organic phases. Similarly, we have cryptands and many other molecules that can be used as a phase transfer catalyst. We will see one by one each of these molecules. We will see examples of tetra-N-butyl ammonium chloride. We can write tetra-N-butyl ammonium chloride as 4 butyl groups attached to nitrogen having a positive charge and a counter ion of chloride. So tetra-N-butyl ammonium chloride, this is used in very many different types of reactions. One such reaction, we can say it as a aldehydes which are di-substituted at alpha carbon. That is, they are possessing one hydrogen atom to alpha carbon atom, like isobutyryl aldehyde. This isobutyryl aldehyde, when it is reacted with say alkyl halide in presence of NaOH, this has problems like the alkyl halide as well as the aldehyde both are soluble in organic solvent, while NaOH is soluble in aqueous medium. So they will not be meeting each other, and because of that the product formation is difficult to hear. Product formation will be difficult, but when we are adding tetra-N-butyl ammonium chloride over here, this will bring this OH minus ion into organic medium and so facilitating the reaction. So we will get this aldehyde, tri-substituted aldehyde, we can obtain it over here. So alkylations can be easily done using tetra-N-butyl ammonium chloride. Similarly, this tetra-N-butyl ammonium chloride is also being reported to be used in Williamson's ether synthesis. We can use this in Williamson's ether synthesis also. Like for example, if we have octanol, if we are adding octanol to butyl chloride, N-butyl chloride in presence of say NaOH, the reaction is formation of ether using Williamson's ether synthesis, but proceeds rarely. But when we are adding tetra-N-butyl ammonium chloride, it will be producing the desired ether in a larger quantities, plus it will also have a byproduct of this type. Byproduct will also be obtained in a smaller quantities. So this is few reactions. Similarly, tetra-N-butyl ammonium chloride is being reported to be used for synthesis of optical brighteners. Optical brighteners such as coumarin derivatives, which are used as optical brighteners. They can be easily synthesized by using this tetra-N-butyl ammonium chloride. Like for example, we can have acetophenone derivative, when reacts with the keto acid, that is acyl chloride, in presence of tetra-N-butyl ammonium chloride. in aqueous potassium carbonate. And benzene, we know that benzene is a carcinogenic, should not be used. You can use other reagent, other solvents also is permitted over here. So this CH3 we will have here as a coumarin synthesis. We have also seen in these coumarins like 4,6-dimethyl, 3-phenyl coumarin can be obtained in excellent yields of 96% by using tetra-butyl ammonium chloride. Tetra-N-butyl ammonium chloride, when we are using it, proceeds with a excellent yield. If we are not using tetra-N-butyl ammonium chloride, this reaction requires anhydrous conditions and the yields are very low. Very low amount of yields are obtained for this optical fiber, but when we are using tetra-N-butyl ammonium chloride, we increase the yield of the products. Similarly, this is being reported to for synthesis of flavones. Flavones, we have seen it in the biogenesis and biosynthesis lectures. There we have biosynthesized flavonoid compounds from shikimate pathway. We have synthesized flavonoid compounds from shikimate pathway. So here we will be the tetra-N-butyl ammonium chloride can be used for synthesizing flavones or flavonoid compounds in the laboratory. Here also we will be using acetophenone derivative and benzoyl chloride in presence of tetra-N-butyl ammonium chloride and base of aqueous potassium carbonate will be giving us this adduct which can be proceeded via ring closing reaction can be carried out here, so that we will be getting the desired flavonoid. This ring closing reaction can be carried out via para-toluene sulfonic acid or PTCA. Here R, we will have an O. Here there will be a pH group. So this is our flavone. So such flavones can be easily synthesized using tetra-N-butyl ammonium chloride. Similarly, we can use this tetra-N-butyl ammonium chloride for many different type of reactions. We can use this. We will see another phase transfer catalyst, that is trimethyl benzyl ammonium chloride or triethyl benzyl ammonium chloride. Instead of these 3 methyl groups, there will be ethyl groups. Then it will be triethyl benzyl ammonium chloride or TEBA. Both will be working in a similar ways. These are being utilized for different types of reactions, like for example in alkylation of N-alkylation of aziridines. N-alkylation of aziridines is highly difficult reaction because we have a 3-membered cyclic ring containing NH in the cycle. So when we are trying to alkylate this nitrogen over here, there is a stress in the ring as it is 3-membered ring. So alkylation will proceed with ring opening reaction. But when we are using this TMBA and an alkyl halide, TMBA and alkyl halide, then in presence of NaOH, this reaction proceeds in aqueous medium very rapidly and we get the alkylated product. So alkylated product can be easily obtained via this phase transfer catalyst trimethyl benzyl ammonium chloride. This is highly difficult reaction if we are doing it in the normal phase. In the normal reactions, when we are trying to do it, it will be undergoing ring opening reaction. So the desired product will be very less. But when we are using trimethyl benzyl ammonium chloride, there is a greater amount of desired product is obtained here. Similarly, N-alkylation of beta lactams is reported using TMBA or TEBA. Like for example, we have what are beta lactams? Beta lactams are nothing but 4-membered cyclic amides. We have it amides when they are cyclic amides we call it as lactams. Similarly, cyclic esters we call it as lactones. Cyclic esters are called as lactones, while cyclic amides are called as lactams. In this reactant, if you see it carefully, we have a acyclic amide and we have a cyclic amide. So cyclic amide, that is, this is lactam, we have it, as well as we have a amide. So similar two groups are present when these are reacting with, say, methoxide over here, and here we have a CHPr, COO. When this reaction proceeds in presence of either TEBA or TMBA, that is trimethyl benzyl ammonium chloride or triethyl benzyl ammonium chloride, we will get the desired product. The CH, here we will have a ester group, and in this side we will have a phenyl ring with a methoxy group at para position. So this product we will be getting it. This product is a part of synthesis of one of the medicinally useful compound called as nocardin, nocardicin A. So this nocardicin A is also having this beta lactam ring, which is alkylated, beta lactam ring alkylated over here. So this part we are getting it here, and this side part is attached to here. So further modifications in the reaction will proceed to synthesis of nocardicin. But the main important reaction over here is, in this case, the alkylation and alkylation of beta lactams, and alkylation of beta lactam without proceeding ring opening reactions. So that can be easily carried out using this TMBA or TEBAs. TMBA is also being reported to be used in carbon intermediate reactions, like for example when we are reacting cyclohexene with chloroform and NaOH. If there is no catalyst being used, in absence of catalyst we get the product, but the product is obtained only in 0.5%, that is almost negligible amount of product is obtained when we are not using any catalyst. But when we are using TMBA as the catalyst, we will get the product, same product we will be obtaining, but this will be in the range of 60 to 70%. So there is a huge difference that occurs when we are using a phase transfer catalyst and when we are not using a phase transfer catalyst. So these are the advantages of phase transfer catalyst. We will see another example of phase transfer catalyst, like Aliquat 336. Aliquat 336 is methyl trioctyl ammonium chloride. This makes available the H2O2 molecule or the HO2 minus anion in the organic medium. Like we know that H2O2 is an excellent oxidizing agent. H2O2 is a very good oxidant. So when it is being used, it is a very good mild oxidizing agent. So we can use this for many different types of reactions. But the problem here is that the H2O2, the active part of H2O2, that is HO2 minus, this HO2 minus is very difficult to bring it into organic medium. So the availability of this anion in organic medium is the one which creates problem for the usage of this H2O2 as an oxidant. But by using Aliquat 336, it has been reported that this H2O2 can be made available in organic medium. Like for example, in Noyori's synthesis of adipic acid. We have seen it in our first lecture on green chemistry that how adipic acid is useful for industry. We require it in a very large quantities. So this adipic acid can be obtained from cyclohexene by Noyori's synthesis when it is treated with H2O2. It oxidizes cyclohexene in presence of a catalytic amount of sodium tungstate and Aliquat 336 as a phase transfer catalyst. When we are using Aliquat 336 as a phase transfer catalyst, there is a ring opening reaction that happens to give adipic acid. This Aliquat 336 is also known as Stark's catalyst, and there are a lot of different reactions that are being reported for the use of Aliquat 336. Similarly, there are other phase transfer catalysts that are being reported here, like for example, we have seen about the crown ethers. Crown ethers are nothing but the cyclic ethers that we are having. The cyclic ethers can be either 5 oxygens or it may have a 6 oxygens. When it is a 6 oxygens, this will be called as 18 crown 6. Like we have it 6 oxygens, we can write it in this way. These are easy to construct. Just join all the oxygens via a 2 carbon chain, that is via ethylene groups. So this becomes a crown ether. Now when we replace the oxygens with nitrogens, it becomes cryptands. So these ethers are the cyclic ethers appears to be like a crown when we see it in a 2 dimension. So these are called as crown ethers. Now what's the important part of this crown ethers is that they are having oxygens in which are projecting inward, that is they are projecting inside, and we know that these oxygens are having 2 lone pairs of electrons. There are 2 lone pairs of electrons on each of these oxygen. So this gives us a concentrated electron cloud inside the crown ether part. So this will be giving us a cloud with which is bearing electrons, that is there is a concentration of negative charge inside the this cyclic ether, cyclic ring, and this facilitates the capture of a cation. Like for example, we can have this 6 crown, we have it, that is there are 6 oxygen atoms are present over here, so we call it as a 18 crown 6, as there are 18 number of atoms are there in this cyclic ring, so we call this as a 18 crown 6 as the name for this. And this 18 crown 6 has a hole created over here, the cavity that is being created, which is sufficient enough to capture potassium ions. Similarly, this is 5 oxygen cyclic ether, so this we call it as a 15 crown 5. This 15 crown 5 has 15 atoms in the cyclic ring, of which 5 are oxygen atoms. So this is 15 crown 5 and has cavity very much similar to accommodate sodium ion. So 15 crown 5 will be accommodating sodium ions, and 18 crown 6 will be accommodating potassium ion. The smaller rings will be accommodating lithium ions, and larger rings will be accommodating the cesium ions and others. But it is generally being used as a 15 crown 5 or 18 crown 6 to capture the potassium ions. Now what happens here is that this is a cyclic ether. So as it is an ether, it is very much soluble in organic medium, and as there is a charges are there, electron clouds are there, so it is also soluble in water also. So it brings the potassium ion from water into the organic medium. Now when this potassium ion that is captured in the 18 crown 6, it is brought into the organic medium, the counter ion of it, that counter ion will also be brought into the organic medium, and this counter ion is the one which acts as a catalyst over here, because this counter ion is freely available now in organic medium, so it acts as a reagent and brings about the reactions there. So here this crown ethers are reported for bringing out many different types of reaction, because they can make available many different types of anions in the organic medium. So we have been reported, there are many examples of reactions catalyzed by crown ethers, such as esterification reactions, like for example we have when this is reacted in presence of 18 crown 6 and acetonitrile, we will get the product as the esters. Similarly, we can use this for synthesis of anhydrides. The potassium salts of acids, when reacts with acyl chlorides, in presence of 18 crown 6. We can write the 18 crown 6 in a short form like this: in presence of solvent acetonitrile at room temperature, the reaction is brought about in 1.5 hours to give us the anhydride. We can bring about the mixed anhydrides also and simple anhydrides also. Similarly, KMnO4 is being reported to be an excellent oxidizing agent, but the permanganate ion is seldomly available in the organic solvent. It has difficulty to be made available in the organic solvent, so the reaction proceeds very slowly. But when phase transfer catalysts like crown ethers are used, they make available this permanganate ion into the organic solvent. Like for example, we have an example of oxidation of alpha pinene. We have biosynthesized alpha pinene in the biosynthesis chapter. There we had studied how this alpha pinene is being synthesized from terpenes. So this alpha pinene, when it is reacted with KMnO4 in presence of 18 crown 6, as it is involving potassium ions, so we will be using 18 crown 6. If there is a sodium ions, then 15 crown 5 we will be using. This gives rise to pinonic acid. This gives rise to pinonic acid, which can be written as, we will have a 4-membered ring with a dimethyl, geminal dimethyl present, and we have a keto group over here, and on this side we have CH2COOH group. So this is pinonic acid. This pinonic acid is obtained in 90% yield when we are using 18 crown 6. So it gives the phase transfer catalyst gives an advantage of higher product yields when they are used for reactions. Similarly, aromatic substitution reactions have also been reported, like for example, in this, if we are using potassium methoxide in presence of 18 crown 6, we will get the substitution reaction where chloro group is substituted by methoxide ions. So in this way, aromatic substitution reactions are can also be carried out very easily. Similarly, elimination reactions have been reported with greater amount of selectivities. Like for example, we have here H and here hydroxy group tosylated, and in this case we have a phenyl ring and a hydrogen. When we are using potassium tertiary butoxide at 50 degrees Celsius, reaction is carried out in presence of 18 crown 6. It gives us two products. One proceeding via syn elimination and the other proceeding via the anti-elimination. Either syn elimination or anti-elimination. When the this 18 crown 6 is not used, that is in absence of 18 crown 6, the product yields are 91% is syn elimination and 9% of anti-elimination is obtained. That is, we get the syn elimination product as a major product. But when we are using 18 crown 6 as a phase transfer catalyst, then we get 30% of syn elimination and 70% of anti-elimination. That is, reactivity can be reversed if we are using phase transfer catalyst, and if we want the other product to be formed, then we do not use the phase transfer catalyst. So here the selectivity can be reversed or can be increased of a certain desired product. So these are few of the examples of phase transfer catalyst 18 crown 6. In this lecture we have seen about the phase transfer catalysts, its advantages, why they are being used, and what is the ease of using this phase transfer catalyst, why industries are preferring the usage of this phase transfer catalyst. We have taken examples of tetra-butyl ammonium chloride, similarly trimethyl benzyl ammonium chloride and triethyl benzyl ammonium chloride, and also we have seen about this crown ethers and Aliquat 336 as the examples of phase transfer catalysts. In the next lecture we will see about the biocatalysts. Thank you.